Energy delivered to a resistor. A 5 microfarad capacitor is charged to a potential difference of 800 volts and then discharged through a resistor. How much energy is delivered to the resistor in the time interval required to fully discharge the capacitor? So, the potential energy stored in the capacitor plus the energy stored in the resistor, the change in the energy stored in the resistor should be equal to 0, so that all of the energy will be transferred to the resistor. Now the initial potential energy stored in the capacitor is 1 over 2 C capacitance epsilon squared, where epsilon is the capacitor initial voltage, which is the electromotive force of the battery. It's connected to assuming that it had zero internal resistance. So we have 1 over 2 capacitance 5 microfarads, 5 times 10 to minus 6 farads, 800 volts, 800 squared gives us 1.6 joules. Now the change in potential energy of the capacitor is final potential energy 0, it will fully discharge, minus the initial potential energy, which is equal to minus the final energy minus the initial energy on the resistor. So that's initially there is no energy on the resistor, so this is minus ER final. So you can see that this is basically the energy dissipated in the resistor that's going to heat. So the amount of heating in the resistor is equal to the initial potential energy of the capacitor, which is 1.6 joules. So that is the amount of energy delivered to the resistor, and it will be turned into internal heating. Okay. Now there's an alternative approach. If we look at the power, the rate of change of energy, dE dt, the energy that is being delivered to the resistor is from time t equals 0 to infinity power dt, and this is basically integral from 0 to infinity I square R dt. We have a time-dependent current, and this is integral from 0 to infinity. Now in the discharge process, remember we had minus q over tau e to the minus t over tau as the current. So that's what we have found in the discharge process. And take its square multiplied by resistance dt. So this will give us q square divided by tau square, which is r square c square, integral 0 to infinity e to the minus 2t over tau dt, and epsilon q was equal to c times epsilon, and tau was equal to rc. So q square over c square is actually epsilon square divided by r square, because q over tau is epsilon over r, you can see here. Then we have the integral minus tau over 2 minus rc over 2 e to the minus 2t over rc, which will be evaluated between time t equals 0 to infinity, and this will give us epsilon square divided by r square. Then we have rc over 2. When we evaluate the exponential at infinity, we obtain 0, so this becomes 0 minus evaluated at 0 is 1, so this will give us minus 1. Minus 1 minus 1 will cancel, so we will have rc over 2. One of the r's will disappear here, so the answer is 1 over 2 C epsilon squared, which is precisely the same answer we have here. It's equal to the initial potential energy stored on the capacitor 1 over 2 C epsilon squared. Okay, so we talked about energy delivered to a resistor, which is going to be turning into heating, internal heating of the resistor. We have a capacitor that is initially charged, and then it gets discharged through the resistor. And how much is the energy that is being delivered to the resistor? Well, it's the initial potential energy stored in the capacitor that is being delivered to the resistor. And we see that the final heating of the resistor, the amount of energy transferred to the resistor, is U initial, which is 1.6 joules, because it is equal to 1 over 2 C epsilon squared. It is, remember that the energy stored on a capacitor is Q squared over 2C, or 1 over 2 CV squared, where V is the voltage across the capacitor. In this case, it's epsilon, which is 800 volts. Alternatively, if you look at the power delivered to the resistor, that is dE dt, the total amount of energy delivered to the resistor, delta ER, will be equal to integral from 0 to infinity P dt, and the power is time varying, it's I square R. And I was basically, this is a discharge process, as we have calculated in the previous video, minus Q over tau e to the minus T over tau. If we substitute this, take its square and perform the integration from 0 to infinity, we obtain exactly the same result, 1/2 C epsilon squared.